So good morning, everybody. You can hear my voice, right? Okay. So I can see Özgür Anıl only. Thank you, Özgür. I hope everybody else is also fine, looking fine. So let's today first wrap up the discrete time frequency response. I mean, like the frequency response of discrete time systems. So why are we studying frequency response? Remember, we are trying to characterize these LTI, linear time invariant systems. And until last week, we characterized them through their impulse response, right? In time domain. And last week we said when the actually input is written in terms of sinusoidals. And actually we know in this class, now you guys all know, you can express actually not any signal, but almost all signals by Fourier series or Fourier transform coefficients. We will study Fourier transform starting probably next week. Next week is our, by the way, 1 week holiday. You guys know it's a break. Probably it's not a holiday for us, right? But still, you guys have a lot of homeworks and projects, I'm sure. But still, we won't have lecture next week. Then the next week, we will start Fourier transform. The reason I'm saying that is for almost any signal, actually, we will we can write it as a sum of sines and cosines or complex exponentials. And that's a very beautiful result, mathematical result. Then that's why here we're looking at, so let's share the screen. Okay, oh, let me write my title, or I could write this later anyways, but today is, okay. All right, so let's just get started. All right, so we said before we learned about h of n impulse response, right, of, let's just a sec, we just impulse response of discrete time systems. Okay, and then we said I can also talk about the frequency response of the same system, and they both characterize or describe the system. Okay, and one nice thing about the frequency response was when the input is given as e to the j, for instance, let's say at a specific frequency, it's a complex exponential, remember, right? At the specific frequency, or it's also called complex sinusoid. And the reason it's important is I just said, because I can actually decompose any signal into these guys, right, with different frequencies. That's important. You guys know now all signals or data have frequency content, and you can write it in terms of these elegant mathematical functions. Okay, so this goes into our system. Before we were saying, hey, x of n goes, and now this little h of n was characterizing my system. Now you see, remember, since last week, we also added equivalently, I can say my frequency response characterizes it. And what was the output actually when the input is such as complex sinusoid? Remember, the actually frequency response is evaluated. Okay, please pay attention. Evaluated there, and I have my signal complex sinusoid as it is coming out. For a real sinusoidal, actually, did we derive this last time, guys? I want to check. Week 9, just a sec. If we didn't derive, we can derive the output to a real sinusoid. Probably not. Do you guys recall? No, we did it, I think. Okay, perfect. Here, I'm looking at last week's notes. As cosine goes in, okay, so I can actually, and remember, then I can say for a real sinusoid, okay, let's say it's now this time, of course, cosine, it would be this guy, right? Cosine omega 0 at n. This is complex sinusoid, this is real sinusoid. When it goes to the system, remember what happens? Just a sec. Okay. The magnitude is modified by, right? The magnitude of the cosine is modified by the magnitude response. You see again evaluated at the input frequency. Of course, if remember by superposition, if there are multiple input frequencies, it will be, of course, summation of all these evaluations, right? H e to the j omega hat 0 magnitude, please pay attention, times cosine itself comes. So the signal, okay, maybe I should use another color. You see the signal is also seen at the output here. So this guy will be also here, cosine, but its phase will be shifted by, right? Here it had 0 phase, but its phase will be shifted by the phase response of this frequency response. So, and it will be also evaluated at, of course, the input frequency. This is the cosine, and let's close the parentheses here. Cosine, and just also pay attention to this, and here this time it's the also the magnitude and the, because I know h can be written as, right, h, because it's a complex function actually. This is not no-brainer, just times polar form, right? Magnitude times, I'm writing it in polar form, magnitude times phase. So it's really this guy. Okay. So we know this. This is really an important result. Let's just, okay. It alters the magnitude of the cosine and the phase of the cosine. So I want to also see, let's do an example now. Did we derive the FAR filter? Yes, I'm gonna use, maybe we've we've done this. Okay, I think I gave you an exercise last time. I hope you did it. Were you guys able to complete this exercise? This was the FIR filter given. You see here, this guy H121. So maybe let me write this example just for your notes. For FIR filter, if you guys solved it, actually, I should not really solve it again. It was an exercise last time. I can maybe just write the result. I asked you, this is last time exercise, I asked you x of n is given x of n, it was 4 plus 3 cosine pi over 3 and minus pi over 2. I'm gonna probably write the answer because it was an exercise. So for your notes, this was last time exercise, right? So I'm hoping you did this. Here y of n was, I'm gonna solve another example, okay? So y of n, did you find this? My question is, did you find the solution? 16 plus 9 cosine pi over 3, and yeah, this was a homework, so I decided not to solve it. You can ask if you have questions. 3 times, okay, it was 9 times, 3 times 152 cosine. So this is the result. I'm asking, like, which principle did you have to use to solve to get this result, guys? Superposition, right? You used superposition using superposition. I'm just waiting for an answer. If you think this is too difficult, we can try to solve it. Did anybody work on this exercise? Mustafa, okay. Thanks for saying it. Mustafa says it's a little bit difficult. So, guys, okay, let's recall. I mean, I have a feeling you guys did not solve it. So, this was the frequency response, right? So, this is the magnitude part. Remember the properties of the discrete time frequency response. It is unique only in this period, right? It's periodic, so I don't need to plot the other parts. This was H, and let's see. Okay, it had linear phase, minus pi to pi. Okay, this is the phase response of the this given filter. This is the FIR filter, given FIR filter in frequency domain, right? Its description in frequency domain. I mean, its time domain representation is filter in frequency domain. We derived this last time, so I'm plotting it. So what I'm going to do is, for instance, for this first part, first signal, let's say this is x1 and this is x2 and this is x3 and, okay? We will use superposition. So what is the response to? I have to find, that means I have to find y1n. That is actually meaning x1n goes to the system, y1n goes out, x2n goes in separately for each component of this signal, right? y2n goes out, x3n goes in, y3n goes out. You see, then in the end, I will be summing these guys. That's it, right? It's clear, I think. So what is the response to x1n? It's a zero frequency signal, right? So I have to look at the frequency response at the zero frequency. Okay? You see phase is zero at that point. What is the magnitude response? It is 4. So y1n will be really x1n times h of 0, right? I mean, actually, it's without the magnitude also. Just a sec. H of e to the j0, which is 4. This guy itself is 4, right? So times 4. So you see the first component is 16. That's how I found this guy. It's clear, right? Now, is it getting clearer? So let's look at the x2n. What is its frequency? This radian frequency, right? Normalized frequency. It's pi over 3, okay? So that would mean, guys, this was 0 frequency. This is pi over 3 frequency. This guy was 7 pi over 8 frequency. So for the second one, pi over 3 frequency, I have to go here and find the read of this value, okay? It's what multiplies or modifies my input. H e to the j pi over 3, whatever its value. So you have to do some math here. Let me also check, guys. So let's say for x1, frequency was 0. For x2 and, okay, this was x1 and our frequency, let's say this was omega 1, omega hat 2 is pi over 3. We evaluated, we know the form of the actually frequency response. So we need this h e to the j pi over 3 is needed. So our h was, let me write it from before, we didn't. So I can show you it from last week. Look at the form of h here above the graph, right? That's what I need to use. So let me write it here for your notes. Actually, h e to the j omega hat, we last time, these are last time, we did this. 2 plus 2 cosine omega hat times e to the minus j omega hat, okay? This was, we found this last time. And that's what I plotted there, right? Up there, actually. That's the h. So I just insert here these pi over 3. Guys, I just found the response. You guys should check it out. Because cosine pi over 3 is 1 over 2, right? That's why actually whatever is in parentheses is 3. Actually, it's very easy to evaluate. So for x3 and r, what is the frequency component? What is the frequency for x3 and for the third part of the signal? What is the frequency? You can say it. I don't know. Your microphones are also not working. Yes, thank you. I mean, from the whole class, I'm asking to everybody. Your mics are not working too, so you guys are chatting, or now you become human beings that are not able to speak out. Okay, thank you, Evren, Özgür. Yes, that's 7 pi over 8. So I need to evaluate. So you guys see here now, I think. I need to go here and find 7 pi over 8. The same here, by the way, right? Actually, for pi over 3, we could have read this phase from here, right? It's minus pi over 3. This was minus pi over 3. Now the same thing here. This value would have been 7 pi over 8. Now this would be h e to the j 7 pi over 8. Okay? So now that would be, let's see, let me write this. 2 plus, I think here you need to use some calculator because there is cosine 7 pi over 8 times e to the minus j 7 pi over 8. Guys, this part you can calculate, just calculate the cosine and it's really just a calculator calculation, right? So we end up with this guy. Then my y of n is really what I wrote because it's really now multiplying or modifying the input. Look at the input cosine. Its magnitude will be, so the x2 was 3 cosine pi over 3 and minus pi over 2. So its magnitude will be multiplied by 3, right? And its phase will be shifted by my minus pi over 3. That's what's happening. So let's write actually maybe y2n is, let's bring it 3 times 3 cosine, right? Just I'm reading from here, pi over 3n. I'm writing its own form already and adding the new. So here are the new modifications, okay? 3 times 3 and right phase due to the system or phase response, system phase response, and this is the multiplying magnitude due to system magnitude response. Okay, I think it should be clear now. So the similarly we should have y3n, which is, let's look the x1n, it was 3 cosine 7 pi over 8n, right? So 3 times 0.152 cosine 7 pi over 8n and minus 7 pi over 8, right? It's exactly what we have. And let's also show these so you guys can see what is happening. And then you add y of n is addition of the 3. Okay? Is it clear now? It's clear, right? Guys. Berke is asking, yes, you can. For instance, numerically we can represent. Also, yeah, if it's an FIR response, you're right. Exactly. It can be written in terms of delta functions. Guys, Berke is asking, this can be done, all of these can be done using impulse response. Great question. Because these are equivalent domains, time domain, frequency domain, whichever is easy for you, you can use. For discrete time signals, FIR filters, where there are just a finite number of filter coefficients like here, it can be easy to do it in both. But for instance, when input is sinusoidal, you see your output in this case, let's say, is very easy to find. Actually, in that other one also, it's going to be easy to find because it will be the impulse response will be written in terms of delta functions and it will be shifts, right? So yeah, it's theoretical possible. It may be what I was trying to say with cosine inputs, the output may be very compact here because we're just modifying the magnitude and shifting its phase. But it is possible with continuous time systems, though, you may, because convolution becomes integrals and your impulse response may be infinite amplitude. Even here also, actually, it could be infinite amplitude, infinite extent, sorry. Then you can, you may not be able to get an analytical solution. So you would have to go through frequency response. Don't go through the time domain convolution. So yeah, I mean, you may get stuck with non-calculatable integrals, so non-integrable functions. So it's better to know, good point actually, so right, better to know which domain to work with, okay? Domain, I should say time or frequency. With efficiently, okay? Efficiently and computationally, let's say. Depending on, this is not right, on your input form. This will become clearer in the continuous time, when we will do the continuous time version. Your input signals, signal components. And actually, we can do both. If the input has, for instance, more like delta functions and both cosines and delta addition, we can just decompose the signal, use frequency response for some part, and use the impulse response for other parts. So I think last time we've seen also this first difference system. I'll give another exercise, but let's just remind you first differencing system, first order difference, right? remember this was a high pass filter, right? Guys, you recall? This is y of n takes the difference between two consecutive samples, right? And we've calculated and we know its impulse response. Of course, very easy. And we calculated its last time we did this, so I'm not doing it again. Let me just write this. And it's very easy. You guys know. I mean, maybe let's write this formula. This will be here k0, 1, h of k, e to the minus j omega, hat k. And we've done this last time. So I'm going to write 2 sine omega hat over 2 e to the minus j hat over 2 minus pi over 2. You see, this was the form of the frequency response from last time. So we did this. We know it was like a high pass looking. So it has 0 at the 0 frequency and its magnitude response. What is its magnitude response? It is actually 2 sine omega hat over 2 pi minus pi here. It was 2 at this point, okay? And it had frequency response, I mean the phase response, sorry, here. Well, let's maybe do it in this way so that we can see. And let's say, let's plot its rapt frequency response. So this is pi over 2. Remember, it's minus pi over omega hat over 2 minus pi over 2. Normally, it would go like this, right? But remember, the goal was to keep this between, actually, it could have stayed between minus pi and pi. But this is, let's see. Here, this is another shift. Very good point. Okay. Guys, this was the reason we are adding, here we're adding a pi in the rapt frequency response here. We add a plus pi because sine, you see, is sine omega hat over 2 changes actually its sign at this point, right? That's why actually we have, what is sine omega hat over 2 normally, guys? Sine 0 pi over 2 1, it would be something like this, right? I mean, it would go in between pi over 2, let's say pi. Just check it out. Put pi in there. Sine pi over 2 is 1. Put minus pi in, I mean, insert into this equation. It's 2, of course, sorry. 2 for this 2 sine omega hat 2. Then there is actually here, this guy was negative, okay? But we pushed it to positive. So there is a minus 1 that is left out. We have to put that into phase, okay? That's where this phase shift is coming in the rapt frequency. Rapt frequency response, I know, is a little bit difficult to understand, but it's really the frequency response itself, but it is being modified by these two things. One, it shouldn't go beyond minus pi to pi. In that case, you just clip it, but you have to put it back using the periodicity by using 2 pi or minus 2 pi. Or if in the magnitude response there is a sign change, you have to bring that minus pi into the phase. That's why here this is being done. Okay. So I'm trying to see. This was actually, no, it should go back down. Here I draw the, guys, because normally it should be up, not down. It's a plus, right? Sorry. Here, what I'm trying to say is normally this guy phase response. Let's write the phase response. What is the phase response here? H. is equal to, actually it's minus omega at order plus pi over 2. Sorry, I said minus, just a second. Go plus pi over 2. So normally, actually, it should go up like this. I mean, it's going into the equation, but that's why there we brought it by pi. Okay? Minus pi. So it's so this is the frequency response. Now I'm asking you as an exercise, use superposition again. Let x of n be, okay, let's write it in this way. I'm giving you again a constant 2 cosine 0.3 pi n minus pi over 4 plus cosine pi n, let's say. So guys, what is the output? Let's try to do it quickly together. I'm asking you calculate the output. What is the response to the constant signal here? 4. Look at the graph. Can you say? I'm waiting. Did you respond, guys? 0. Thanks, Evren. Yes. Guys, look, I already here marked it for you. So it will be y of n 4 times 0. You see, because constant signal, that's the lowest frequency signal, right? So it's a low frequency component, no frequency oscillation. So actually, that is 0. The response to 4 is zeroed out. So this is, you see, showing the high frequency or high pass filter. So aspect. Because this is a high pass filter, it will either suppress fully or attenuate low frequencies. What happens here is, for instance, when x1n, which is equal to 0, goes into this system, 0 goes out. Okay, that's what I'm trying to say. This is the meaning of high pass or low pass. Is this clear? Okay, for the second one, let's see. I have to go to 0.3 pi. Just here, go 0.3 pi, whatever that is, evaluate. Guys, from here, bring it here. Whatever that value is, bring it here. And also bring its phase here, wherever this is, 0.3 pi, and this was 0. Okay, then this guy should come into the cosine 0.3 pi and minus pi over 4. Okay, it should come here. Plus phase at, this should be pi, by the way, I just realized. 0.3 pi. This is the cosine now, new cosine. You see, it has a new phase. Okay? From the phase plot, I can read it. Now, the third one, the third component, what is the frequency? It is pi. What is the magnitude response at pi? Please read it. It's 1 times, it should come in here, 2, right? Yes, 2. Just read it off here, 2. I just marked it for you. Now, cosine pi over pi n plus, what is the phase at pi? 0, right? So there was no phase shift at that point. Okay, this is the idea. All right, so I think that's fine. One more thing. for this frequency response of, I mean, but is this clear? I hope this is clear. Frequency response of these finite difference, I mean, difference equations. So let's say frequency response these difference equation systems. Remember, its most general form is this guy, but in this course, we're not really studying these infinite impulse response, these recursive filters, where I have also, you see, shifts of the output, but we are using only these finite impulse response systems on the right-hand side. So for us, we assume, I should write this, don't get confused. This is the general form of these difference equation systems. But we assume in this course, A0 is 1 only. A0 is 1, AK are 0. K not equal to 0, okay? Let's remember what we do. So that's why we have Y of n equals, this is the FIR, remember, the finite impulse response system, minus K. So maybe I could just say, give an example here. Actually, H would be, maybe let's do this. If remember, when, I mean, this is what we do, right? When X of n is a complex sinusoid, Y of n is really H of e to the j omega hat n. So now if we insert or substitute this into the equations, okay, I could just want to write the general form, substitute now into here. Where do we substitute it? Here to this equation. General difference equation system, substitute into here, guys. So this is what we have. K, AK, H e to the j omega hat. It's a shift, right? I know how a shift takes place. M minus K omega hat. So I'm using really this guy now. Sorry, this guy I'm using and inserting it into this equation, top equation. Okay. And this is really K, BK e to the j omega hat and minus K. Okay. Now I'm using also, you realize, time invariance, right? Time invariance of these systems. X of n minus K. So I shift, actually, you see e to the j omega hat n minus K. Okay. So now from here, because these guys, this guy did not depend on K, I can take it out. What I'm trying to show is this, guys. Take this out. From here, also I can take out e to the j omega hat n's out here. So let's write, okay, in that case, hat n e to the j omega hat n does not depend on k, exactly. Sum k a k e to the minus j omega hat k, right? Equals sum k b k minus j omega hat k. What I'm trying to find is this, and h actually is, bring this guy to the other side as a denominator. From here we can see that actually h, the frequency response, is sum k bk. This will become a little bit more clearer when we study Fourier transform, but it's maybe a little bit ahead, but still the point I'm trying to make is we've already seen the numerator part, right? But I can express the frequency response for this general difference equation systems in this way. However, for us, of course, again, for us, because A0 is 1 and all other AK are 0, it's again H e to the j omega hat is really just K bk e to the minus j omega hat k. So maybe guys just know the general one, but I mean don't get confused. Okay, so let's maybe do an example. So for this guy, one more example. An FIR system running average 6-point running average system y of n, that would be x of n plus, you see it's a large one, I mean a long one, goes all the way to n minus 1. This is 6-point running average filter, right? And the coefficients are, so for h of n, if I ask you what it is, you guys would write, this is for n equals 0, 1 over 6, 1 over 6, right? 6 of these you need to write. This is h of n. What is the frequency response? You just have to apply the rule or the property of h, which is, I mean, the definition of h, which is here at the bottom, on the right, bottom right. So it's gonna be, let's write it, 1 over 6. In the 1 over 6 parentheses, actually 1 plus e to the minus j omega hat plus e to the minus j omega hat 2. Right? This is what I have. Now let's manipulate this a little bit. I'm showing this on purpose because maybe it may be a little bit more difficult to manipulate here. So guys, we will be grouping these together like this. So this guy, this guy, this guy. So it will be in this way. 1 plus e to the minus j omega hat plus, now this guy, group them together in this way, minus j 2 omega hat, yeah. So that will again be 1 plus e to the minus j omega hat. You'll see the trick. Again, the same thing here. This time, e to the minus j 4 omega hat. I will have 1 plus e to the minus j omega hat. Okay? So you see now I can really have two parts. 1 plus e to the minus j omega hat and 1 plus it's, you see, a lot of fun mathematics, not difficult. It's just math here. And here also, again, do the same trick here. Right? We've done this last time also, I think. With the needed trick, we can go from this to take it into the e to the minus j omega hat over 2 parentheses. And you can do this. Then you'll see it's really this guy. Same thing here. This time take into the 2 omega minus j omega hat 2 parentheses. I will have e to the j omega hat 2 plus 1 plus e to the minus j omega hat 2. So you see the cosine coming, right? From here. This will be really 1 plus 2 cosine 2 omega hat. It's a lot of Euler formula and manipulation of these polynomials in e to the j omega hat. Okay, that's it, actually. So you see our h now is, let's write the full thing, 1 over 3. Let me see, I think we can merge the phase, e to the minus j pi over 2 the omega hat cosine omega hat over 2 times 2 cosine 2 omega hat plus 1. Okay, this is it. So from here, this is a little bit difficult example. I did it on purpose. Like manipulation is difficult. So what is the magnitude response? 1/3. So magnitude response will come from the cosines here, right? The phase, leave it to the phase response. Cosine omega hat over 2 plus 1. You have to check here what is the overall magnitude, guys. So here, this guy, so maybe let's do this in the, it will be -2 to 2, right, in this range. So overall, for instance, this guy will be between -1 to 3. So let's say this guy is there. This guy's magnitude is in 0, 1. So actually, when you multiply these, the magnitude will be in 0, 3, right? I mean, it has to be also, like, because I'm taking an absolute value here. So magnitude will be in 0, 3, but we have to have, I think here, a -1 that has to be accounted. Okay? So I want to draw this just because it is educational. And I'll give you an exercise for the difference version of this. Okay? After this, we can give a break and then we can continue with the other parts. Okay. So how you can draw it is this way, guys. So just draw the cosine first. Omega hat, cosine, 1 minus 1. This is cosine omega hat. Now, what is 2 cosine 2 omega hat? I'm trying to replicate this. Whatever, terms are there, I'm trying to find it here. That will be, let's say, I mean, it won't be to scale, so just, I mean, when I put 2 here, of course, 1 you see up there, but it's fine. So this is pi, let's say. This was pi over 2. In this case, guys, it's gonna go like this. Okay, it's difficult to draw a little bit, so it's gonna be in this way. This is pi over 2, all the way to pi. Okay, this is 2 cosine. You can do this. I mean, this is again high school math. Probably I'm really scaling some functions, right? Okay, this should be looking like a nice cosine, but now I can add 1 to this, and it's gonna shift up. 1 plus 2 cosine 2 omega hat. I've done this before, so I'm looking and doing it quickly. So it's gonna really go up to 3, right? Because it's a shift by 1, and it's gonna really this time do something like this, right? Goes to 3 at this point, pi over 2, and it's gonna come to -1 at this point. Okay, that's it. Now I need also to multiply this guy by cosine omega hat over 2. You see, I'm trying to, at the bottom, look at this form of the function. This is really mathematics, calculus I'm doing right now. What is cosine omega hat over 2? It should be just a cosine coming down, right, from 1 to 0 at pi. Now multiply the 2. Multiply the 2. It's the resulting frequency response. But I need to multiply, but I need to also put an absolute value. Multiply and also put the absolute value, okay? Then it's gonna have this form. So there will be, this is pi over 2, but I need pi over 3 because this was pi over 3. This was 2 pi over 3. Now it's gonna jump. So look at this negative part. Guys, it's gonna have this. Then this peak, you know, in the negative, it's gonna be here. Pi over 3, 2 pi over 3. Now, this is, you see, suppressing this part too much, so it's gonna be really getting smaller, pi. So you see, this is really, this is 1. What is this? Because magnitude 0, 3, this was 1 over 3 here. The whole thing's magnitude is in 0, 1. So actually, really, it's 1 to 0. This is exactly what I plotted here, okay? Plot this. So we plotted this, plot this. Here it is. This was actually a little bit mathematical exercise. But important thing, there are zeros you see here at multiples of pi over 3 for this filter. This was a 6-point running average filter. That's multiples of 2 pi over 6 actually. So pi over 3. Zeros at multiples of 2 pi over 6. So it will be 2 pi over 6k. Okay, so let's write it. 2 pi over 6k. So in general, for instance, L point running average filter, in general, for instance, let's say L point running average filter, they will be at 2 pi over Lk. Zeros at, okay. But you see, what is the form of this? Let me ask you, what is the, when you look at this, let me redraw it here. Okay, I'm redrawing. H is this magnitude response, right? It's something like this. Here, here, here. Pi is here, sorry. This was omega hat. This is pi. Okay, 0, but 1. What form of filter is this? It's a low pass, right? Running average filter. This has a low pass form. I mean, look at the here. I mean, at least it's larger here at the lower frequencies around 0. And you see it is suppressing down the high frequencies, right? Okay, let me, for your notes, just also plot this guy. The phase was minus 5 omega hat over 2. You guys can see normally this would have been in this range. Without wrapping it, it would be something like this, right? Pi. I mean, just if I'm just plotting it in the 0 pi, because let's see. I mean, I can easily just continue in the other way, but minus 5 pi over 2, of course, at this point. This would be unwrapped frequency response. But the wrapped one would be, again, a little bit interesting to draw this. It's going down, guys. But at pi over 3, it has to. Okay, let's maybe make my pi over 3 a little bit here. Pi over 3, 2 pi over 3, and pi comes down here. And at this point, because there was a sign change, it makes a jump, plus pi jump, okay? So actually this guy is going to be something like this. Guys, good news is typically the numerical tools, libraries Probably this is in NumPy, for instance, in Python. Those will work this for you. There are Fourier transform functions there too. But you may, when you plot these things, you may see like this rapt frequency response. You should understand what's going on. Okay, and in this course, of course, you are supposed to know how to do this from scratch. But you should know the fundamentals of something. So that's why you should not please think, hey, the software is already going to do this for me. Why should I know? You should. I mean, you are the scientist, you are the engineer. Okay, if you don't know this, who is going to develop these tools? Okay, you can't always be the user. You cannot, you can never be. I mean, you should use things, of course, reuse, but you should understand what's going on beneath. So here, guys, this is the rapt frequency response. Okay. Why is it taking these plus pi jumps? Remember, because there is a sign change at these points, in the sign change in the magnitude response. Okay? I mean, this is happening because there exists a sign change at this point, at this value, let's say, this omega hat value in the magnitude response. That's why we have those. We want to account for those. And a sign is a sign change, meaning then because -1, which is equal to e to the j pi, or it could be also e to the minus j pi, depending on how we keep this in 0 pi range. Okay, I think this stays between minus pi and pi range. Also, don't get confused. This was for the top plots. This was actually, I hope, -5 pi over 2 was here. But I mean, this is again the phase rapt frequency response. Anyways, if I give you, for instance, now an input function signal, you can read it off from the magnitude response, right? Its values, like how you would obtain the output. If I give you an input, you would go here and calculate the corresponding frequency response values at the corresponding frequencies of the input. Okay. So for instance, exercise, I'm gonna stop now, but exercise, if I give you now, if we had, I mean, it's a challenge, can you do this system? Just for comparison, I'm going to give you the difference system for this one. Y of n is 1/6. It's taking, for instance, x of n minus x of n minus 1 plus x of n minus 2 minus x of n minus 3. You see, takes the 6 most recent inputs and forms their first order differences. For instance, this is another system. So takes 6 most recent inputs and forms the differences, forms the first order differences. So here, maybe let me note, we said this is low pass, so it attenuates psi frequencies. What do you expect now? Because this was an averaging filter. What do you expect now, guys? What kind of a filter would you expect? I mean, pay attention to these differences, right? Probably you guys already answered correctly. A high pass, right? Yes. Now, this time, it would attenuate the low frequencies, right? Attenuate low frequency components in the input, of course. I mean, this is a system, right? This is a system form. This is a system. It would attenuate low frequency components in the input. Maybe for your notes, I can just write the result and you guys can actually, because you can calculate this all the way here. Please check, calculate to find h, let's write, of e to the j omega hat 1/3 e to the j pi over 2 e to the minus j. Actually, it looks a little bit similar, you see. The phase looks similar with a pi over 2 shift. Now I have a sign, you see, because that attenuates the frequencies at the low frequencies. And this part is the same, actually, the second cosine 2 omega hat plus 1 part. You see, now what happened is there is a sign. This part is the same, 1 plus 2 cosine omega hat. You will replace this cosine omega hat over 2 by a sine, and you guys will find so you will see that I have exactly very similar. This is the component here, okay, in the magnitude, and we will have a sign, which is of course something like this. Let's say this is pi, and that is, let's say, 1. This is the sine omega hat over 2. Now multiply them, we will get the magnitude response. This guy will be this time the other way around. So let's suppress the low frequencies and keep the high frequencies. Let's say this is pi over 3. You see, very symmetrical. I mean, these will be really similar to what we had before, but maybe a little bit less. And this is 1. This is the magnitude response, high pass characteristic. Okay. So you see, for high frequencies, we have a gain of unity, actually the highest frequency or close to. For high frequencies, close to pi, this H gain or magnitude response has a gain close to 1. Let's say, I mean, not 1, but I think you got the point. And you guys can look at the frequency, the phase part. It's really the pi over 2 shifted version of the previous one, right? This is the phase response. And I think that should be enough. We've really studied this discrete time part. Okay, I think, yeah, we can give a break and then start with the continuous time Fourier, not Fourier transform, frequency response, okay? So it's 9:40. Okay, I think we went, yeah, we've done 1 hour, almost 1 hour 20 and 10 minutes. So maybe we should give a longer break, guys, right? Give a longer break, maybe come back around 10. So let's pause recording for the break. So, okay, we're back from the break. So now, guys, we will move on to characterize continuous time systems in the frequency domain now. Very similar, but some mathematical differences. So it won't be very difficult. So that's why we can do this part a little bit quicker. Frequency response of continuous time systems. But the concepts are the same. And I think this was chapter 10 in the SP first book. DSP first is, as the name implies, is digital signal processing, so it won't have continuous time frequency response, only discrete time. But for mathematical completeness, I want us to do this. By the way, remember why are we making these distinctions? Because there are like continuous time systems overall, like for instance, if the signal is an analog physical signal, right? Like the voice signal, light signals, I'm just making up, electrical signals, biological signals, they are all continuous time signals, right? Physical signals. If this was a big, large continuous time system, remember, lately, actually, we have a lot of digital signals, systems, DSP, digital signal processing system, processor, for instance. Here, that's why we typically have a continuous to discrete, and actually, we studied this part, right, before, until here, in a way, we were studying this part as the discrete time system. But if the input is a, for instance, physical continuous time signal, then we need to deal with a continuous time system, right? And also we may either be fine with just staying with this discrete time signal, or we may want to go back to the continuous time, like in this voice example. Remember, music, for instance, your music files, they are converted into MP3 format. You can do processing there, and then you can, through a speaker system, play it back, right? Then that would be actually a discrete to continuous converter, which is a conversion which is taking place in the speaker system. Remember, here this is an example. To continuous discrete is a microphone recording your voice and converting it into a sequence of numbers, right? Digitizing it. So continuous time systems, let's say this time, in time domain, remember, we've studied these guys, and it's really when x of t goes in this whole continuous time system, remember, we were saying if it's LTI, impulse response again characterizes it. Now, what if, again, my question is, if x of t is a sinusoidal, okay, sinusoidal signal, I think you guys will guess output, again, will be a sinusoidal. That was the point we've seen, actually. Output is, again, a sinusoidal. This is what we've studied just in the first hour and last week. Sinusoidal, but modified, right? Well, but modified sinusoidal. That's important. So now we will start similarly. This time, this is, remember, a continuous time complex sinusoid, right? It will go into the system. This time, guys, we will denote this frequency response in continuous domain by h of j omega, not with omega hat, okay? And I will have similarly, very similar to what we've seen before, a modified, you see, modified form of the sinusoid. And the actually frequency response is evaluated at omega 0. The input frequency is evaluated at input, this is at input frequency, okay? Here in this case, it's just one frequency. Okay, so let's again derive the relation between actually impulse response and frequency response. We will, okay, let's say here this guy is only a function of frequency variable W, but this time W don't have to be between minus pi to pi. We will look at that. Okay, so guys, let's see, let's do this. So let x of n, not x of n, okay, we've been doing discrete time, so x of t. is a e to the j phi, okay, with some phase, this complex exponential omega t, let's say, goes through, let's say, this system denoted currently by h of t. We've learned, what did we learn last time? If I know h of t, y of t is given by, we know, y of t is given by the convolution sum, right? Yeah, so we should say x of t convolved with h of t, which is, so infinity, let's say h of tau, because it's commutative, you can change, of course, these two effects, t minus tau d tau. Now insert x of t here. Insert it here. Okay, it's not maybe, but I think you get the point, so let's just write it. Y of t is integral minus infinity to infinity a. Okay, let's first write h of tau. A e to the j phi e to the j omega t minus tau d tau, right? So a e to the j phi and j omega t could go out because that is not a function of the tau. So I have really a e to the j phi e to the j omega t. You see what I'm left with here. Okay, so this is, as you guys can guess, this is exactly what we've done last time. This is defined to be the frequency response. You see, actually, this is Fourier transform of, again, the impulse response. Okay? Fourier transform, maybe for your notes. We will study Fourier transform next time. So, but I mean, don't get confused, but just know ahead of time, this is the form of the Fourier transform. So it's really, you see the input itself again, the sinusoidal itself. But whenever x of t is only this sinusoidal, right? It's valid only for these times h, not e to the, but h of t. But only for sinusoidal. I mean, it's not like for any other signal, okay? This is valid for, this multiplication is only valid for sinusoidal. So this h of j omega, which is equal to minus infinity to infinity, h of t e to the minus j omega t dt. This is the frequency response of the LTI system. Just a sec, guys. Okay, so this is the frequency response of LTI system given by h of t. So we've just now seen actually h of t in time domain, again equivalently, this time h of j omega in frequency domain. Okay, represent. So if this is frequency domain, representation of the system. So representation of the system. Okay. Again, this h is a complex function, right? I can write it in polar form. So I can say h of j omega is a magnitude. I mean, this is really exactly the same as before in polar form. You guys see here, omega this time is, omega is really a, again, before it was also a continuous variable, but continuous variable in minus infinity to infinity. So this time h of j omega will not be periodic with 2 pi. Maybe let's write this actually in terms of properties. Properties of h of j omega, guys, it's very similar. as before. I think I should write this is important. Continuous time frequency response is not periodic with 2 pi. Okay? But recall discrete time version. It was periodic, right? So this would mean, I mean, I should say hj omega plus 2 pi is not equal to h of j omega as before. And omega, like I said, is in between. Omega is free to take all values in between minus infinity to infinity, okay? I mean, you can show this, guys. Just write this from the definition, apply the definition. You may be like, why? Apply the definition. Okay. To infinity, h of t e to the j omega plus 2 pi. Just add 2 pi to omega and let's see what happens, right? That's the goal. This was minus, of course. I'm applying the definition with omega plus 2 pi. And what is this? E to the minus j omega t times e to the minus j 2 pi t. Here, the important thing is this is not equal to 1, right? Because t is a continuous variable. Before n was integer, it was always multiples of 2 pi. That's the difference. Okay? So guys, note this, please. E to the j 2 pi t plus minus doesn't matter is not equal to 1 for all t. That's the thing. Because now t is a continuous variable, continuous time variable. Okay? This is important, I think. So also then we will plot h in between all frequencies. Now I'll give an example. So for instance, h of j omega, it can be plotted for all, again, plus infinity to minus infinity. Of course, wherever it's non-zero, but recall, again, discrete time version. Recall in discrete time. Actually, our h e to the j omega hat, it was just actually valid between this range. It was repeating itself. This is different, okay? So valid for all W or for all, maybe I've tried to say plot should be plotted for all. Plot should be for all W. Here, remember, because this was because H was h e to the j omega hat, the discrete time version was periodic with 2 pi. This is probably one of the important differences, but other than that, actually, guys, everything is almost the same. So for instance, for a real sinusoid, another property for a real sinusoid, I won't rederive this, but I think you guys can guess what the output will be. A cosine, because it's very similar derivation. Let's say I input as continuous time sinusoid like this, right? Into the system with this frequency response. What is y of t? Exactly as before. A times, it will be modified by the magnitude response, right? Times, okay, times cosine, okay, let's bring it here, t plus phi plus the phase response. Okay, of course, evaluated at the frequencies that are already in the signal. Okay, so this will be same as before. So there is nothing to repeat there, to derive. This is also same. If h of t is real, guys, j omega, there is a conjugate symmetry. When we have a real system, impulse response is real, we have conjugate symmetry we have conjugate symmetry in the frequency response. This is again as same as before. And remember, we go even further. The magnitude response has even symmetry. Even symmetry means just replace, for instance, the variable by minus, and it still be the same function, even symmetry. And the phase response has the odd symmetry, remember? That would mean now H minus j omega, or j omega is minus of that, let's say. Let's write it. I could put minus on this side, but let's not put that here. And minus H of, okay, phase response of minus H minus j omega. Here it's important. This is odd symmetry. I mean, it's important to note this minuses here. This minus and this minus, okay? I mean, this is mathematics, from mathematics. Conjugate symmetry, even symmetry, and odd symmetry, okay? And superposition rule applies, of course, for the same property. Superposition rule. Sum of sinusoids goes to the system. Sum of sinusoids go out. Sum of sinusoids again. Sum of sinusoid inputs, let's say, sum of sinusoid outputs for each of them. Okay? So maybe let me write this again for your notes. If I had n of these cosines with different phases and different frequencies, right? My output y of t, actually, let's write it here just for using the whole line, y of t, k 1 to n, it's gonna be, okay, 1, ak multiplied by the magnitude response, right? With the given frequency though. This is important, guys. Note this, okay? And cosine, now the phase will be affected by, of course, the corresponding phase response, right? Evaluated at the given phase frequency, or I should say. Okay, this is, okay, now the other property. So let's do some examples now, guys. Okay, by the way, let me plot something here just for not, I mean, this is trying to say it's going all over, but also let's write this with color properties, because for the notes, properties of Hj omega. Okay. All right. I think now let's do an example. For instance, I will give you an LTI system. LTI, given LTI system. For instance, this was given and it's asking for the frequency response. It's really about applying the definition minus infinity to infinity, right? Take the integral. This actually definition of the of t e to the t dt. This is actually also the Fourier transform. So it's infinity to infinity 2 e to the minus 2 t u of t. T. Now u of t just has to start from 0 to, this is gonna be just a integral of an exponential, right? Minus j, this will be minus j omega plus 2, right? T. So we should just now do, let me see. Actually, it's minus should be out. Both were minus. Sorry, minus should be out. So minus j 2 plus omega t, right? J omega, yeah. Sorry, guys. Just add these up. Come on. Minus 2 plus j omega t. Okay. Just look at. I was correct, but with a plus sign in the first one. Okay. That's good. To dt. Right? Now do the math here. It's the integral. So this guy's integral. 2 can go out, of course. 2, then I have minus here, 2 plus j omega, right? I'm doing the integral. The exponential is again here still minus 2 plus j omega t from 0 to infinity. So in the end, I should not have any t's, of course, in the frequency response, right? So we should have, when I put infinity, that's a 0, right? So 2 over 2 plus j omega, let's say. That's a minus 2, 1. And sorry, 0. And when I put 0, it's a 1. Okay, so it's really 2 over 2 plus j omega. Okay? So now let's take it to the complex plane. This guy, because I want to write it as a magnitude times phase. That's my goal now, guys. I want to find what is this, because I want to plot it afterwards, and I want to find these two guys, like the phase and the magnitude response. So numerator, denominator, right? They have both complex numbers. I mean, numerator is 2 here, but denominator is 2 plus j omega. So let's just write it here. Two in the real. J omega, this is imaginary, right? The j plane, so it goes to omega here. The magnitude, right? I just have to look at the magnitude. It's 4 plus omega squared in square root. So that's what we have. So then I have really 2 over 4 plus omega squared, right? For the magnitude. Is it clear? From the, always go to the complex plane, then it's very clear actually if you go to the complex plane. The phase is, guys, a phase of the numerator minus phase of the denominator. Okay? That's how we, think about this in polar form. Minus phase of the denominator. Phase is phase of this guy, 2 plus j omega. What is phase of this? This is really arctangent omega over 2. Right? I mean, just here, look. It's this phase, theta. Right? Omega over 2. This is omega, this is 2. That's the angle, right? Is it clear when you look at the complex plane? Great. So now we have to, so it's going to be really, what is the phase of 2? It is 0. So actually, you see, it's minus arctangent omega over 2. Okay? Now let's plot these two guys. Both the magnitude and phase response, let's plot. Let me write it again for this page. H was, the magnitude response was 2 over 4 plus omega squared. Let's plot it here. I mean, you can plot these things. This is really calculus. It's going to be something like that, like this. You see, it's, you know, a function inversely proportional to square root omega square or omega like. So this guy, I think, is 1 at, because insert 0 to W, it's 1 at the 0, right? Frequency. And for instance, at 2, frequency 2, it's going to have 1 over square root 2. The same for, it's a symmetric one. Remember, this is a real impulse response, right? So which property applies? This third property. So it's real. I have even symmetry in the magnitude response, odd symmetry in the phase response. So actually, I'm expecting this even symmetry. This is even symmetric. And the same for the this guy. It has to be, of course, this guy has to be odd symmetric. H j omega. What was it? It was minus arctangent W over 2, right? Just check exactly. So let's plot this guy. Let me try to plot it nice. It has two sides. So this guy, all omega. So I have to do minus arctangent. It is something like this, right? I mean, this is an asymptotical approach to pi over 2 and minus pi over 2. Okay? So this is 0. This is the phase response. Sometimes with the magnitude response, you see a log plot. But first, let me ask you, let's maybe don't do a log, but you may see log plots sometimes, guys. Sometimes you may see log plots, or sometimes even it's log plot. Take the log of the both axes. That's it actually. Log plot. This is really a side note. You may see it, so that's why I'm really showing it. So I mean, log plot is log. It plots log W versus this log of this guy, log of the H magnitude response. I mean, it's gonna look like probably something like this, but I mean, important thing is the form of the, of course, filter doesn't change. This is what type of a filter is this? Is the question. We have to look at the magnitude response, right? Response form or shape. Again, low pass, right? Yeah, you guys, I think, already answered. Low pass. Keeps the low frequencies. This is a low pass filter or system. I mean, filter because it's really filtering the inputs, high frequencies, right? So now I think we can maybe, let's see, we've done this already. We could maybe use a superposition principle. So now I can ask you this. Again, you see, guys, it's very similar. That's why I'm doing it a little bit fast. Example, use superposition principle to find the output of the LTI system. I mean, actually, it's the same guy, h of t. Okay, I have given 2e to the minus t u of t, but let's say I have given now e to the minus t u of t when x of t, okay, I'll give you an x of t now, h of t, this is y of t. We know it's actually frequency response. We just calculated without the 2 now. It was 2 plus j omega. I mean, it just scales it a little bit, right? I mean, that's almost the same thing. Now I want us to calculate for a specific input, given input. Let's give it on the next page. I want you guys to calculate the output. So let's do this. So let x of t equals 5 plus 8 cosine 2t plus pi over 3 plus, here this is important. One of you asked this in the first hour. I have 3 components in this signal. Please pay attention, everybody. 3 components. There is a constant one, which is 0 frequency. So I should go by frequency response. Second component is a sinusoid. It's wiser, easier to go with a frequency response. But for the third one, it's easier to use the impulse response. So you see, you can mix and match. It's a superposition. I can treat each component as I like, right? So for the third component, we will calculate its output in the time domain, and then we can sum everything up. Okay? That's the idea. So let's say, guys, this is x1 of t. This is x2 of t. This is x3 of t. So now let's start with x1 of t. Its frequency is 0, right? It's a constant signal. So y1 of t is, maybe let's say here, 5 times h of the frequency response evaluated at 0, right? Guys, here it should be 1 over. Maybe I could change this whole derivation to 1 and get rid of that 2. But I think you guys get it, right? It will be 1 over 2 here at 0. Because now my h of t is half of the h of t we were using, right? This guy is 1 over 2, so it's really gonna be 5 over 2 output. Is it clear, guys? Okay, this is good. Now for x2 of t, what is the frequency? It's 2 hertz, right? Let's say, or radians per second. Actually, hertz would be over 2 pi version of this, right? Before, guys, I was not writing the unit. It was radians, unitless. Now it's radians per second. It's better to write. So here I need to calculate. From here, I know I should really calculate h, the frequency response at 2, frequency 2. Okay? This will be 1 over 2 plus j2. Now I should convert this to polar form, okay? To polar form, remember from here, the magnitude response is 1 over 4 plus 4, which is 2 square root 2, right? Then I need hj2, the frequency, 0 for the numerator minus arctangent 2 over 2, right? Which is pi over 4. So which is equal to minus pi over 4, right? This is it. Now from here, y2 of t will be, remember, it will be 8 times the magnitude response, 1 over 2 square root 2, right? Now cosine 2t plus pi over 3 minus pi over 4. Modulate or modify the input by, you see, the phase and the magnitude. You see, it's much easier to work with the frequency response for the first 2 components. Now the third component, let's write this. For x3 was 0.1. Now y3 will be convolution, okay? x3 of t convolved with h of t. Because I've seen delta here. Delta is the function I like to work with convolution. Remember, that just shifts, right? It's convolution. Easier, let's write, to do convolution. So time domain processing. Therefore, time domain processing is preferred for the third signal component. Okay. So we should just say, guys, and do this, convolution. What is it? It's x3. What was x3? It's 3 delta t minus 0.1 convolves the h of t. So actually I would have 3 h of t minus 0.1, right? Shifted, modified, which is actually equal to, what is h of t? Go back. It's e to the minus 2t u of t shifted by 0.1. That's it. 3 e to the minus 2 t minus 0.1 u of t minus 0.1. That's it. This is my y3 of t. Now from here, my output of the system is really y1 of t. So it's really superposition, y2 of t plus y3 of t. Okay? This is it actually. You see, we were doing this for discrete time. Now we did the same thing for continuous time. Okay? All right. So let's do one more example. Okay, then we can again talk about ideal filters, cascade and parallel connections. That should be fine. Actually, great. Any questions until here, guys? All right. Maybe before, so. All right. So, guys, all right, so let me add a page here, a few more pages. Okay. So this was another example just to really exercise more on this. So probably I can do this quickly and let you do the exercise. It's the same idea. I mean, actually now I'm thinking, now let's say here it's given h of j omega. You see this will be, this will also have the same form in the numerator, but we are given this, okay? We are given the frequency response. It's really easy. You should just use superposition. Use superposition to find the output. Maybe just for the notes, let's do this. So, I mean, here, what is happening here is, guys, x of t goes to the system, h whose frequency response is given, and we want to calculate the output, right? That's what we are after. Again, I can say this is x1 of t, this is x2 of t, okay? And I can just write x1 of t is equal to, it was given as 2 cosine t, of course. And for this guy, what is W1? It's 1 radians per second, right? It's 1 radians per second. I need to calculate then h at j1, which is equal to 2 plus j over 1 minus j. Here there is some manipulation in the complex plane. Guys, multiply this by 1 over j. So at j1 is really 2 plus j2. Let me write it openly so when studying you guys can see what is happening. 1 minus j squared. It's really in the end 1 plus j3 over 2. And you can write this from the complex plane. Go to complex plane, guys. So it's really 1 over 2 here and 3 over 2 here, right? I mean, 1 over 2 should be a little bit less here. Real and imaginary, okay? And this is it actually, right? I need to really find the angle and the magnitude, polar form, right? It's clear, right, everybody? This is it. So what are those? Guys, we calculated it for you. It's really in polar form. That's the idea. 1.58. I mean, it can be rough, of course. 3, 2. arctangent. So you need to do theta is arctangent 3 over 2 over 1 over 2. I mean arctangent 3, right? Of course. It's arctangent 3. And that happens to be this guy. Okay. So for x2, now x2 of t, w to the its frequency is 3 radians per second. Do the same math. Okay, I'll very quickly write it out. J3 is 2 plus J3 over 1 minus J3. And you guys can use a calculator like I did up there. Please check this. You can use a calculator, okay? And these are approximate values, of course. Check this exercise. Okay, so now, guys, from here, the result is, okay, y1 of t, let's first write. Y1 of t is 2hj1. So take the input and modify it by the magnitude response at the frequency of that input and write the cosine part. It's t cosine t. It should be modified by the phase. Where is the phase? Okay, I'm using these two, guys. So this was already 158, right? 158. Now this is t plus, no, minus, sorry. 0.32, let's say, right? And this was 158. So in the end, it's gonna be really 2 times 158 cosine t minus 0.32. You see, this is the response. For the y2t, it's gonna be hj3 magnitude response cosine 3t plus 1.57, and let's check the, it's here minus 0.25, and this was 114, so this is really 114 cosine 3t, whatever that sum is, okay? What is it, guys? 23132. So that's it. And then from here, y of t is really from superposition, due superposition. I mean, it was a very similar example, but here the manipulation in the complex plane was a little bit tough. I mean, more difficult. That's it. Okay. I think this should be fine. Now let's, any questions here until here, guys? Are we clear? Right? It's much fun, actually. It's really not difficult. So what are ideal filters? These are frequency selective systems. Remember, this is one of the goals of a system. Selective systems. I think we've looked at them a little bit in the discrete time, but ideal means, actually, guys, one, they have value of 1 in the pass band. Pass band is the desired frequencies. So we will idealize these, all these filters, remember. Okay, I couldn't go there, sorry. Guys, just a sec, I mean, this is a low pass filter, but now we will idealize it, okay? These were not ideal, these are practical filters, so more practical. Okay, have value 1 in the desired frequencies to have, I mean, it was not exactly practical, by the way, that was an infinite pulse response, but still, analog wise, it can be created, for instance, that's typically created by RC type circuits, have value of 0 for stop band or in the stop band, let's say. Okay. These are the undesired parts. So for instance, okay, let's say these are I and 2I. Now the first one is ideal low pass filter. It's gonna be this guy. Now we are free to go to minus infinity to infinity, right? And I will have this guy. It's if it's a real filter, it should be symmetric, remember. It's one here. I'm actually showing the magnitude response, but I mean, assume the phase is either a linear phase or something like that. So this is the cutoff frequency. Here it's important. This is cutoff frequency. And this is the pass band. Okay? Pass band, you see I have one value, and everywhere else I have 0 value for the filter. Okay, pass band. And these are stop bands. Stop bands. Band. And I think last time we looked at practical filters. Here there is no transition. I mean, if I were to have a practical real filter, probably this will look like, I mean, analog filter, right? We are in the continuous time, so there will be a transition period, and you see from pass band to stop band, you can't just go in an infinite jump. This was the transition. Band, pass band, practical filter, recall. This is mainly, I think, important for electrical electronic engineers, but it's good for you to know these systems in mathematical form and to how to implement them numerically, right? Because you are computer engineers, you guys use the computer or processors, for instance, digital signal processors to process these. You won't be building them with circuits or things like that, right? I mean, you are the computer guys, so computing guys. Pass band. So in a real filter, but you should still have an idea about other engineering fields, guys. Always have curiosity and interest in science, both physics, chemistry. For instance, I really like to follow the Nobel Prize every year. Like, right, there are very exciting developments. You should feel an interest because you are computer scientists, computer engineers. You are all connected. And I always say now you are in the middle of all these disciplines. You are in a very important, very prestigious position because all of them need you for their computational needs, especially with this AI revolution. So you guys should at least be nice, respect other disciplines, and have an understanding and interest. Okay? So that's why, please, when I draw such a practical filter, why should I learn this? It's not like that. Already probably some of you may have hobbies like these too. If you're a musician, I was giving you this example of the equalizer. Remember, in the first few weeks, you know how to work with these filters, actually, bandpass filters. Now we will draw that too. So here you see the difference. There is no transition band. No, here there is a transition band, no transition band in an ideal filter. These are good to idealize and for abstraction, for our manipulation and design analysis. So that's why we need to know or model these ideal filters too. So low pass filter, H low pass, let's say, of j omega is defined by, I think we did this for discrete time, but let's also do it for the continuous time. Omega, for omega, absolute omega less than or equal to the cutoff, it's 1, otherwise it's 0. But let's write it maybe as omega greater than. Okay, this would be the mathematical definition. Now the ideal high pass filter, guys, let's write it here. Ideal high pass filter. Now this guy will be, I think you can imagine its form. I mean, it's gonna be symmetric with the cutoffs, of course. Again, omega cutoff minus omega cutoff, 0 here. Let's say this is high pass, H of high pass. This is it. So it's 0 in the stop band and 1 in the pass band. Okay? All right. So I can also say right here, H high pass of J omega is 1 minus H low pass of J omega. You can see that, right? If I had a constant 1 filter and all pass filter. Yeah, an all pass filter, I can say all pass. That would be all ones, right? As the name implies, it's all ones. I mean, goes all the way to infinity, it's 1. This is an all pass filter. I mean, it's just an identity. I mean, it's all ones everywhere. So what else? We can look at an ideal delay filter. Now we know all pass. For instance, by the way, are these ideal high pass and low pass filters clear? It's suppressing the low frequencies in the high pass. Okay. So here now, the third, let's say, an ideal delay filter. I think you guys already ideal delay system, let's say, or filter. System, filter, I use exchangeably. Remember, this guy was really y of t is the delayed form of the input. My h of t was really a shifted delta to that position, right? Now its form, graphical form, remember. Okay, h of j omega, what is it, by the way? Let's do this. Minus infinity to infinity. Let's apply the formula, the definition. Okay, this is equal to minus infinity to infinity delta t minus t0 e to the minus j omega t dt. Remember, we know this to be, this guy is a sampler, right? And integrate out, it really samples the function it is multiplying at that time point. Okay? So the frequency response is this complex exponential, but actually with this T0, now you will see what that T0 is. It's what is the magnitude response? Maybe actually from here, okay. What is the magnitude response? 1, right? 1. So that's where that all pass comes. So it's an all pass. All pass magnitude response. Yeah, it doesn't do any change in the magnitude. That's what it says. The phase response is actually the filter itself here. The phase response, j omega is really this guy, t0. Or maybe I should say, no, minus omega t0 is better to say, right? Minus omega t0. It's that guy. So now let's plot this. This is the phase response, and it's gonna be called the linear phase. Okay, with slope slope is minus t0, right? So whatever frequency you gave me, I can find its corresponding. I'm just making up, for instance, if it's minus 2.5 or it's, let's say, it should be anything, just don't get confused. It's 3 frequency, I mean, this is radian per second, by the way, 3 radians per second. You can just read it off from here, the amount of phase shift, right? That's it. So this would be minus 3t0. This is the amount of phase shift it introduces. Shift or delay in, let's say, phase shift it introduces. Okay? This is a linear phase system. Remember, we've seen this, recall. Okay? Guys, just a sec. All right, so this is a linear phase system. We said, what else can we do? We can now, guys, combine these systems. Actually, it's now we will come to, that will bring us to cascade, but okay, maybe before that I should do ideal bandpass and ideal bandstop filters. Let's do these. Which one were we at? 3. So 4 is ideal bandpass filter. We've seen this also last time. So here, however, we don't have the periodicity, okay? So that's why, I mean, it should be symmetric, by the way. I just draw this. This is H bandpass filter, J omega 0. Let's say 1 omega 2 minus omega 1 minus omega 2 and 1. So let's write this also mathematically. This would be bandpass filter J omega, which is 1 when our frequencies are between, okay, let's maybe write this a little bit in the middle, omega O2 and omega O1, right? And 0 elsewhere, right? This is the mathematical definition. You see again, guys, the pass band and the stop band. So there is also ideal band stop filter. It will be vice versa, 1 minus this guy. Band stop filter, it will be really H band stop filter is 1 minus H band pass filter. So I'll draw it just for our notes. Again, this time just imagine subtracting that filter from 1. Okay, all these guys, by the way, have a unit, our x-axis, okay? So it's gonna be really something like this. 1 here, stopping someplace, and then again 1. This is really passing, trying to pass everything other than a set of frequencies. But in the first one, it's trying to pass only the frequencies in this range, right? Just passes, plus minus, of course, just passes these frequencies, eliminates everything else. This is why it's called, it's a bandpass filter. For instance, recall the audio equalizer. If you are a musician, do we have musicians in the class? You guys know this. Like I was saying, for instance, you may want to pick a certain frequency ranges like the bass or the treble or some certain high frequencies, and you may want to boost them, right? Or suppress the others. So this is something you guys know. Okay, and again, let me give some parameters, right? These are the parameters of the filter, by the way, right? These frequencies, guys, are these frequencies, cutoff frequencies, These are parameters to be found, to be selected. By design, of course, depends on you. Okay. This bandstop filter has another name sometimes, notch filter. Maybe again, some of you may have heard it. It's when this stop band is very narrow. Very narrow stop band, guys. It's gonna be like this. Let's say here. Now it's really stopping very certain range. I mean, it's really no-brainer. It's really the same thing, but maybe let's like this, draw this a little bit nicer. So when, again, this is omega 1, omega 2, but it has a very narrow stop band. These are some, notation, terminology we've learned. So notch filter has a very narrow stop band. These guys. And this one. This was the stop band here. Again, stop band. Band of frequencies, right? You can see that. And these are the pass bands again. So now we can start connecting these things in series and in parallel. That's the last thing we want to study for today from this continuous time frequency response. Are we clear until here? It's very meaningful, right? Intuitive stuff. So let's also do that. Let's do this actually first, cascade, and let's do the cascade connection. It's very safe. Actually, it's similar, so I won't repeat the formulas, cascade and parallel connection of LTI systems. The rules are same, I mean. Rules are same before, meaning, remember, in the cascade connection, the frequency response, when you add them series, it's multiplied, right? In time domain, it's convolved impulse responses. Parallel, it's always added. Okay? It's the same rule. So I really don't need to repeat, but still, let's just say LTI1, LTI2. Okay? So let's say this is the first system, the second system, and if my, again, complex exponential goes in, this would be, I know now, right? Okay, h1 j omega times e to the j omega t, and then this would be h2 j omega, h1 j omega, e to the j omega t. So I know already the overall, right? That's the idea. So guys, I think we should just say overall response, frequency response, h overall j omega. If you have many of these guys, h1 j omega, h2, and also multiplication is commutative. So you see I'm changing also associative, so order of these. If you have n filters, for instance, pons for n filters in cascade. It's the same as before. And similarly, for the addition, the parallel, it will be the addition. Okay? Similarly, this is cascade. Parallel, I think you guys again remember, I have LTI1, LTI2, LTIN, and filters. They in parallel process my input. You can do the math. Again, guys, the output will be h1 j omega plus h2 j omega, right? Plus hn j omega times e to the j omega t. So actually, this is the overall. This time you see it's the addition, right? We've done this, but I'm just doing this just for your notes. So I want to motivate actually now. I know maybe we could have motivated before, but say, why am I doing these connections? Say, guys, we have a cheap, low quality, low pass filter. Okay, cheap, and cheap is not always bad, but here in this case, cheap, bad, low pass filter. Let's say it's this guy with the frequency response with h given in this way. Let's say in this way. Okay, it's 2 at 0 frequency, and let's say it's 1 at omega 0 and minus omega 0. Okay. I mean, bad meaning in terms of cheap or bad here in this case is if it's a low pass filter, I don't want really large tails or, you know, magnitude response values here, right? The gain should be smaller here. That's why, I mean, gain is not as small as I want here. And also pass band, remember the ideal low pass filter. I want ideally 1 in the pass band, so low band, and 0 in the other side, right? The high frequency. Now, can I combine a set of filters in cascade, such of, because these are cheap, I can buy many of these, let's say. I can connect these in series. That's the idea. So let's do. So what we will be doing is connect, for instance, 2 of these. H1, H1. Okay. Maybe this will help me now to get, guys, something like, hopefully this is getting a little bit, you know, flatter here, right? And maybe the cutoff is here, by the way. This is cutoff. I want to really keep in between. This is my pass band. That's what I'm trying to say. So let's bring those cutoff frequencies. This will be the goal. Let's just redraw. Or maybe not like this. I'm trying to, maybe it's now getting a little bit flatter. Okay, and it's also, it should be getting a little bit less in the stop band. Okay, so maybe, okay, this was 8-0 for the whole thing overall. Maybe now connect 10 of these, cascade. This was not enough. 10 of these filters, because they are cheap, I was able to buy them. I was able to buy 10 of these. Now, I may have, I mean, the goal is to have, this is something you would have to, of course, connect them and in cascade and see, but minus omega 0, omega 0. Hopefully, I have something like, you see what I'm trying to say? I mean, I'm trying to make the filter smaller in the stop band, make it more, maybe this is H10 of j omega, 10 of these. So my goal is maybe to make it flatter here, okay? Smaller transition here. I mean, these are all design criteria. And also here, I want to have closer to 0 in the stop band. Okay, this is omega, by the way. Okay? So, I mean, the goal is when I do this, for the why, you may be asking, why am I connecting these things? That's why I'm saying I get a better filter, right? I get a better low pass filter when I cascade connect, for instance, okay? You can try this actually, Yusuf. This could be an actually good homework or exercise, right?
Okay, hocam,
We can note this at least, yeah. And if there is room in the homeworks, we can do this. Same thing, guys. One final example. For instance, this is a usage of cascade connection. I can use addition, this parallel connection, to create a bandpass filter from low-pass filters, two low-pass filters. For instance, I am not able to buy a bandpass filter. So let's do that and then leave you. Actually, I thought we would leave early, but we're not. Anyways, so example, now you have two cheap low-pass filters, okay, with cutoff frequencies like this. You were able to find these guys. F1 is 10 kilohertz, let's say. The second guy is at 20 kilohertz. Now my question is, make a bandpass filter, okay, with passband between these two, actually, in 10 to 20 kilohertz, okay? You can do it now. You can say, hey, I can use a parallel connection. Let's do it. You will be using this. Say, I will use my two H1, H2. I need here, it's a block diagram, of course. I can easily invert, but I need an inverter here also, guys. So you should really note this minus here, minus plus, okay? And y of t goes out. The overall, let's look at the overall filter. The overall filter response is, we know this, right? H2 j omega minus H1 j omega, right? Because we know it's addition, but it's now also added by an inversion. So now let's look at the plot. Let's plot H2 first, because we'll subtract the other from that. Let's maybe make this, let's plot it a little bit centered. Omega. I'm trying to plot it here, so I want to. Okay, so let's say this is my H2. I'm showing ideal filters, of course. I mean, it will not be ideal, but still, let's see the idea here. So here it's around, okay, here I'm showing the F in kilohertz. You know the equivalence, so doesn't matter. Kilohertz. So this was 20 minus 20. Now plot the second guy. Okay, maybe let's plot it somewhere here. Again, F kilohertz, the filter 1, H1 j omega. It will have passband in the plus minus 10, right? Kilohertz with 1. Now the overall frequency response is exactly what I want, right? It's gonna be subtract from each other, this guy. 0 in between, and again, and 0 everywhere else. This is 1. So passband is really here, and stop band. This is a bandpass filter, right? This HO j omega is the bandpass filter that was targeted, right? I mean, that was our goal actually. So we can obtain this bandpass filter by, I mean, here my goal was to show you why you would mix and match, you know, add or connect in series or in parallel these different filters. You may create new filters, right? By these connections. Is the idea clear? Good. Thank you, Özgür and Evren. At least I'm seeing some nodes, which is nice. I think this should be fine for our continuous time frequency response. I mean, frequency response of continuous time filters. Of course, when you look at this page, there is no time variable here, right? I mean, it's really all about frequencies. Frequency response is a function which does not relate to a time variable. Okay, I think you can start the quiz now, and guys, have a good break next week. Have a good holiday also. So let me stop the recording. See you next time, guys.